So this is section 7E, we'll call it, because it's an extra section that's not in your text from chapter 7, Kepler's laws of motion. So we're going to identify the three laws of motion, we're going to validate and prove the third law, and then discuss satellites and derive the orbital velocity equation. So to start, let's take a look at the first law. The first law tells us that the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one focus. And a focus is a focal point. So let's start by looking at Pluto. Pluto's a little more obvious. So here's Pluto's orbit, very elliptical. Its eccentricity much greater than that of the Earth or Mars. So for Pluto, here's what's happening. The sun is at one focus point. Other point is empty space. Well, why is that true? Because think about it. A circle has one center. And a circle is really defined as a locus of points equidistant from the center, that distance being the radius. Well, in this case, we have to consider the fact that like this distance here is different from this distance here, which is different from this distance here. So you don't have a center to this. You have two focal points. And an ellipse, you can say, also has a major and a minor axis. And those are terms like diameters, if you will. They're not diameters at all, but the idea of the width and the height of the ellipse is what we're talking about here. So what's interesting to recognize is that the Earth's orbit is pretty much a circle. I mean, it's very close. We say that it's elliptical, and you see this when you're younger in these diagrams that really exaggerate the Earth's orbital pattern. And in a lot of diagrams, you'll see the Earth's pattern or the Earth's orbit look like this, when in reality, it's actually very close to a circle. Its eccentricity being close to zero. So it's not obvious to the naked eye, yet this is actually an ellipse. Okay, it is actually an ellipse. The second law tells us that an imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal time intervals. So let's take a look at this one and see. On the left here, we'll see the Earth traveling around the sun. And it's not in the exaggerated form which we're seeing on the right over here. And what we'll notice is that there's 12 different areas here, probably representing in this diagram the 12 months, but obviously the 12 months are not equally spaced. Some months have 31 days, some months have 30, one month even has 29 or 28 days, depending on the year. So we shouldn't necessarily assume that they're months, but we can assume, because of this law, that these are equal time intervals. So from here to here, a certain amount of time passes. Well, the same amount of time passes from here to here, which passes from here to here, from here to here, from here to here. So what's happening is this. Say it's a month, right? It takes the Earth a month to go from here to here. Well, it also takes the Earth a month to go from here to here. So when the Earth is closer to the sun, it's going to travel a longer arc length, and when it's further from the sun, it travels a shorter arc length. Because this is like a big slice of pizza. This is like a short, wide slice of pizza. But these areas are the same. These areas are the same. These areas are the same, assuming that these are equal time intervals for each of these different spacings. So what we'll recognize, though, again, is that the orbital speed here is greater because it covers a longer arc length or a longer distance in the same time period as this part. So this is a low orbital speed. This is a higher orbital speed. And on the right, you can see exactly what I'm mentioning here. If the time interval it takes to go from here to here is the same as this time interval, we can conclude that this area must be equal to this area, or vice versa. Okay? The converse is also true. Again, this is an exaggerated orbital shape of the Earth. And this doesn't have to be the Earth. Let's call this Pluto, and then it wouldn't really be exaggerated very much because Pluto is much closer to an ellipse than the Earth is. Now, a follow-up thing to mention is the fact that, and this is a common misconception, it's not really one of Kepler's laws, but it's something that's worth mentioning when we talk about celestial bodies and the Earth specifically. The Earth in the northern hemisphere actually has summer when it's further from the sun. So right here is summer for the northern hemisphere. And when it's closer to the sun, it's actually winter for the northern hemisphere. And here's the reason. The Earth is on a 23.5 degree tilt. So if I blew up the size of the Earth, here's the Earth there. Well, this is what the axis would look like. There's the North Pole and there's the South Pole. But when we're on this side here, here's the Earth, and it's still, that's the equator right there, right? There's the North Pole and there's the South Pole at the bottom. So I'm drawing in the equator, obviously. That's the equator here and here. So what happens is when the Earth is on this side of the sun, the direct rays hit the northern hemisphere at a higher angle of incoming solar radiation than on this side where the southern hemisphere receives those intense sun rays, which is why the northern and southern hemisphere have swapped seasons. When we have winter, which is right here, the southern hemisphere has summer because it faces the direction of the sun there. So it's not the distance from the sun that matters. You don't get closer to the sun and further in causing the seasons, but the tilt of the axis is what causes the seasons. This also, as a result, causes 24 hours of darkness or 24 hours of daylight at certain times of the year near the poles, near the southern and northern poles of the Earth. You get days at a time where it's all daylight or it's all darkness for 24 hours. And that's, again, the result of the tilting axis. The third law says that the ratio of the squares of the periods, time period of revolution, of any two planets is equal to the ratio of the cubes of their average distance being like the fact that it's a ellipse. It's not going to always be the same distance from the sun. But what we'll recognize here is that this ratio is constant for all the planets. So if we take the time it takes squared over the average distance from the sun cubed, so this is in seconds, right? The period in seconds and the distance average in meters. What we'll get pretty much the same answer for all the planets. And this is using a period in seconds and an average distance in meters. We can see down here, we're going to do it in a moment as well. But what you're going to recognize is that you square this and divide it by the cube of this, you get this number. The same thing occurs for Mars. Okay, and again, these are off by a little bit, but they're approximately the same number. This number is sometimes known as Kepler's constant, but depending upon the units, if it's in seconds and meters, this is the number. But if I look down here where I look at my period in years, Earth years specifically, and I look at my average distance as like an AU, where an AU is one Earth distance from the sun. So if we look at it down here, Kepler's constant changes, but let's take a look at that. So again, AU standing for Earth's average distance from the sun. The Earth takes 1 year to revolve around the sun. The Earth's average distance is 1 AU. Now, Mercury is closer to the sun, so it has a shorter period. It doesn't go as far, and its average distance is not as far. But still, when you square this and divide it by the cube of this, you get a number close to 1. So Kepler's constant here is around 1 for all of these using these units. And you'll recognize as the planet gets further, average distance from the sun is 39 Earth distances. Its period is much greater. So these things are definitely related, and they both are directly related, or they're directly related to one another. But what we'll recognize is that the square of the period over the cube of the average distance always comes out to be around the same number for all planets. So what we're going to do next is prove this third law. Okay, we're going to prove that it's a constant. The ratio of t squared over r cubed is a constant. So to do that, we need to start by assuming that m1 is the planet's mass and m2 is the sun's mass. That's our first assumption we're going to make. We then have to say to ourselves, okay, well, we have centripetal force, which we know of, and the centripetal force formula is the mass of the orbiting object, m1, the planet, times its velocity squared over the average distance or the radius. Now, we can assume for this the Earth maybe because it's approximately circular, because we know centripetal force is really related to circular motion. So we're making the assumption that the orbit is close enough to a circle that we can use this information. But we also know this fact, that the gravitational pull between the sun and the Earth is g, mass of the planet, or the Earth in this case, it doesn't matter, mass of the sun over the distance between their centers squared. Now, if we're looking at the orbit around the sun, we could assume here that this r value we're looking at is the same thing for both of these. Okay, this is the distance from the center of the sun from the Earth. This is the same thing here. So these are the same. Well, remember that centripetal force is always provided by something. Like, we talked about how a roller coaster going through a loop-de-loop stays on the track because of normal force. You can talk about how an electron is in orbit because of the electrostatic force. An object that's attached to a rope is in circular motion because of the force of tension, while planets are in orbit because of the force of gravity. So this centripetal force is caused by gravity. So these are the same things. So we can go ahead and set those two equal to each other. What we'll recognize right away is that we have some cancellations to make for sure. The mass of the planet cancels on both sides, so now we only have the mass of the sun involved. This r cancels with one of these r's, leaving an r behind, which makes this v squared equals gm2 over r. Well, we have to consider the fact that we're approximately circular in orbit, so we can calculate the velocity or the speed, the orbital speed in this case, by thinking about the fact that it travels in some sort of a circular orbit. So if I want to find the circumference here over the time period, that will be what the speed is. Why am I able to use circumference? Because the circumference is the distance traveled when the planet is doing its revolution around the sun. Okay, so that's the circumference. Circumference is 2 pi r. So let's go ahead and replace circumference with 2 pi r. And that still equals gm2 over r. Let's go ahead and square everything. 4 pi squared r squared over t squared equals gm2 over r. And next what I'm going to do is this. I'm going to go ahead and take this equation here, and I'm going to rearrange it so that it looks like t squared over r cubed. So I need to move this t up here by multiplying both sides by t squared. Divide this on both sides, gm2, so pretty much move it down here, so those can kind of flip-flop. And then take this r squared and divide both sides by r squared, which in essence puts it down here. So that gives me the following. 4 pi squared over gm2 equal t squared over r cubed. Well, take a look. This is what we were looking at for Kepler's third law here. For Kepler's third law, we said that the ratio of the time period of revolution squared to the average distance from the sun cubed is the same for all planets. Well, why does this make that statement, or why does that validate that statement? Because look, this is a constant, this is a constant, this is a gravitational constant, 6.67 times 10 to the negative 11, and this is the mass of the sun, which is also a constant. So it turns out that this ratio is going to always equal some constant. So no matter what planet you use, you're going to get the same constant every time, and this actually turns out to be Kepler's constant right here that we're talking about. Next, we have to take a look at a satellite, and first start by defining what a satellite is. And most people think of a satellite, obviously, as like this metallic object in the sky that sends in these telecommunication signals, and that is an example of a satellite. But a satellite in general is any celestial body that orbits another body. For example, the Earth is a satellite of the Sun, but the Moon is a satellite of the Earth. Well, so are those telecommunication devices, but they're just called satellites. They're artificial satellites that just transmit EM waves back and forth between two locations on the Earth. We just happen to be familiar with them, but any satellite. So the question is, how does a satellite stay in orbit? Like for something like the Moon, obviously, we didn't put it there in orbit. It is in orbit, but how do we put man-made satellites, really is what we're talking about, in orbit? So let's take a look at how a satellite stays in orbit. So the whole principle behind this, concerning satellites, it's pretty much a projectile, a satellite. That's to say that a satellite, only has gravity acting on it when it's moving through our gravitational field. So once it's launched into orbit, the only force governing its motion is the force of gravity. And Newton was the first to theorize that a projectile launched with enough speed would actually end up orbiting the Earth, because it would start to fall. Think about it. You launch a projectile. If you launch it with enough speed, it only starts to fall, and it starts to fall and fall, and maybe it falls at the same rate that the Earth curves. And the Earth's curvature is that for every 8,000 meters along the horizon or horizontal, it falls 5 meters. So if you can get a projectile to move at this exact curvature, it would end up just going right around the Earth, coming all the way back around. It would be like constantly falling, but falling at the perfect rate. So the whole idea here is that if the launch speed is too small, it'll eventually fall back to the Earth. It might stay up for a while, but it'll fall. If it's launched with sufficient speed, the projectile falls toward the Earth, but at the same exact rate that the Earth curves. So therefore, it would pretty much stay at the same height above the Earth, and it would continue in this circular path. And really, it makes the projectile concentric with the circumference of the Earth. They share the same center. So again, really what's happening here is that at every point in the trajectory, the satellite is falling toward the Earth. But because the Earth is curved, it never really reaches the Earth because it falls at the same curvature of that of the actual Earth. So next we'll take a look at the derivation of the orbital velocity of a satellite. And this is going to be very similar to what we just did, where we proved t squared over r cubed being a constant, Kepler's constant. So m1 this time we'll call a satellite, and m2 the central object. Earlier we called this the sun, and we called this the planet. It's really the same thing again. So we can start with the exact same governing equations, fc and fg. I could set them equal, so I'm going to jump right to this part here. Again, centripetal force acting on the satellite equals the gravitational force, because again, it's really just a projectile falling. So what provides this? It's gravity. We cancel through, r cancels with that, the satellite mass cancels with the satellite mass, leaving v squared equals gm2 over r. So if we want to solve for v, we take the square root of both sides, the square root cancels the square, and we get v equals the square root of m2 over r. So m2 happens to be the central object in this case, and r is the actual distance from center to center between the satellite and the central object. What's interesting to note here is that the orbital velocity of a satellite is independent of the mass of the satellite. And granted, it will take more fuel and more energy to get that object moving to the right velocity, but once it's in that motion, it does not matter. The actual mass of the satellite has no effect on the orbital velocity that it will be traveling with.